Hello. In the previous clips we have taken a look at control system design using root locus and before that using Bode plots, and when we did the design we did not make any particular assumption about the specific nature of the disturbance that was affecting our system or the specific kind of plant that we are dealing with. So therefore we had to rely upon generic controllers such as the ones that were available off the shelf, namely the proportional type, proportional integral or PID or lead lag or one of these controllers, or we had to synthesize controllers of a structure different from all of these which satisfied our particular requirements. Now since we did not make any assumption about our knowledge of the plant or its environment, there was only so much that we could accomplish as far as control engineering was concerned. So the ideal of getting x of t to be equal to r of t of course had to be compromised. It had to be compromised a little bit, but nevertheless compromised on account of the fact that we did not have any precise information about the plant or its environment. So one can therefore expect that if one knew something about the plant or one knew something about the reference that we are interested to track or the disturbance that we are interested to reject, we should be able to do a little bit better than what we could do with the generic controllers that we have seen so far. So this lecture, this clip therefore would focus on discussion of controllers for systems where something more is known about either the plant or its environment or the reference that we wish to track, and the hope is that this extra knowledge will allow us to do better as control engineers and perhaps even accomplish the ideal of perfectly rejecting a disturbance or perfectly tracking a certain reference. So what we will see in this clip is that if we happen to know the precise frequency at which the disturbance might be affecting us, or the precise frequency of reference that we are expected to track, or the precise set of frequencies of references that we are expected to track, then we can exploit this information to do much better than what the generic controllers that we discussed in the previous clips allow us to do. To illustrate the capability of this, let us first revisit the problem that we had taken up when we were doing control design using Bode plots. So in that problem we were interested to reject disturbances and track a certain reference. Specifically, to refresh your memory, we had a plant which was given by P of s is equal to 10 by s by 10 plus 1 times s by 50 plus 1 times s by 300 plus 1. So this was the plant that we had considered, and we were interested to reject a disturbance of frequency 0.2 radian per second and track a reference of frequency 0.1 radian per second. Subsequently we also expressed our desire to design a controller which rejected disturbance at around 10 radians per second, so at this particular frequency, and we wanted it also to be rejected by 99%. So we wanted only 1% of that disturbance to affect our output. Now let us say we were not interested even in that 1% of the disturbance affecting our output. We wanted perfect rejection of this disturbance. Is that possible? Well, in general, if you are told that this disturbance has a certain frequency spectrum, it is not, all the energy is not concentrated at a single frequency, but rather it is distributed over a certain set of frequencies, and this distribution is not known ahead of time, then there is not much more that you can do than what was done by the PID controller that we designed. So this PID controller allowed us to achieve a sufficiently high loop gain in the frequency range of 10 radian per second, and that allowed us to reject this disturbance by the required amount of about 99%. But suppose you are told that this disturbance is actually a sinusoidal disturbance, so there is only one frequency in this disturbance and that is 10 radian per second. Of course this still does not mean that we know everything about a disturbance. For instance, we do not know its amplitude, we do not know its phase, but we do happen to know that its frequency is exactly 10 radians per second. The question is, can we employ this extra piece of information to do much better than what this particular controller, the PID controller, did? So even that 1% of leakage of disturbance that is happening into the output, can that be plugged, can that be avoided by employing this extra knowledge that this disturbance is at a single frequency, namely 10 radian per second, and we want to reject this perfectly. Now it is not unreasonable to expect this kind of a scenario to arise in practice, because generally if you think of, for example, the problem of vibration isolation, where you have a very sensitive setup that you want to isolate from the rest of the environment, then generally the vibrations that this setup would feel would be due to some motor that is running nearby, or some footsteps of people and so on and so forth. Footsteps of course do not have a specific frequency spectrum, so we cannot employ this technique, but if this disturbance, if the setup is being shaken by a motor, then the speed of that motor is generally fixed, and therefore we know precisely the frequency content of the disturbance that is affecting our system. It will be a periodic signal of period equal to the rotation speed of that motor or its higher harmonics. So therefore there are occasions in practice where we might be fortunate enough to find that the disturbance has a particular fixed time period, or even better, it might be a sinusoidal disturbance of a particular fixed frequency, and that is the specific problem that we are considering here. So suppose we know that this disturbance is at 10 radian per second, can we do something to reject it perfectly? Now to understand if we can reject this perfectly or not, let us first take a step back and see why this particular controller is not able to reject it perfectly. To do that, what I would do is first write down the transfer function that relates the output x of s to the disturbance d of s, and that, as you know, is given by 1 by 1 plus c of s times p of s. Therefore our x of s would be equal to d of s divided by 1 plus c of s p of s. Now our controller transfer function has already been written out in the previous slide. It is given by c of s is equal to 6 times s plus 1 by s times s by 170 plus 1 times s by 1700 plus 1, and p of s is the plant, which is given by 10 by s by 10 plus 1 times s by 50 plus 1 times s by 300 plus 1. Now x of t of course will be the Laplace inverse of x of s, which is going to be the Laplace inverse of this term here on the right, namely d of s by 1 plus c of s times p of s. Now if we know that our disturbance d of s is a sinusoidal signal of frequency 10 radian per second or some particular frequency omega, then we know that the Laplace transform of this disturbance would be of the form a1s plus a2 divided by s square plus omega square, where omega is that particular frequency of oscillation of this disturbance. In our particular case it happens to be 10 radian per second. Now these constants a1 and a2 are unknown because we do not know the magnitude and the phase of the disturbance, we just happen to know its frequency omega, namely 10 radian per second. But we can exploit that and write x of t as Laplace inverse of a1s plus a2 divided by 1 plus c of s times p of s times s square plus omega square. So I have just substituted d of s with the term a1s plus a2 divided by s square plus omega square to get this term. Now to obtain the Laplace inverse, we can use the method of partial fractions, which we talked about in a few clips back. So essentially I can write this as Laplace inverse of some constant b1 by s plus p1 plus b2 by s plus p2 and so on and so forth plus bn by s plus pn, where p1 to pn are the n poles of the closed loop system, or in other words the zeros of the term 1 plus C of s times P of s. So zeros of 1 plus C times P are given by P1 to Pn. So I can use partial fractions to write out the entire term within the bracket of this Laplace inverse as this plus a constant, let me call it C1, divided by s plus j omega, because the term s square plus omega square can be factorized as s plus j omega times s minus j omega. So when I write it out as a partial fraction, it would be of the form C1 plus s plus j omega, C1 by s plus j omega plus C1 bar by s minus j omega. So this is going to be the general partial fractions expansion of the term within the bracket. Now if we take the Laplace inverse of the first term, we would get b1 e power minus p1 t, and the second term would be b2 e power minus p2 t, and so on and so forth up to bn e power minus pn t, and we would have c1 e power minus j omega t plus c1 bar e power j omega t. So this is going to be the expansion. To remind you, the reason we are undertaking this analysis was to determine why we are having non-zero error, why we are unable to get the disturbance to be rejected perfectly by the controller that we had designed earlier, namely the PID controller. And if we look at the time domain response, we see that all these terms b1 e power minus p1 t etc. are all decaying functions of time. Why is that so? That is because as control engineers we have designed our closed loop system to be stable, which means by definition that the zeros of 1 plus C of s times P of s will always be by design on the left half of the complex plane. So they will all have decaying exponential terms. Therefore what this indicates is that if I wait long enough, then all the terms that are related to the response due to the plant's poles will all decay down to 0. So if I wait long enough in the limit at time t tends to infinity, every single term b1 e power minus p1 t etc. all the way up to bn e power minus pn t will all die down and go to 0. What will remain and persist for all time, however, is this term here, the term that is because of the sinusoidal forcing. The question now then is, can we choose a controller structure that will make this term go away? Now to answer that question, let us come back to the expression for x of s. The expression for x of s is that x of s is equal to a1s plus a2 divided by 1 plus c of s times p of s times s square plus omega square. Now we discovered in the previous slide that the real culprit, the one that is responsible for having that 1% leakage of the disturbance at the output, was this term s square plus omega square. The response due to the other poles die down because our closed loop system has been designed to be stable. Therefore if at all we can find a way to make this term disappear in the transfer function that relates the input to the disturbance, then we are home free. There is a possibility for us to get the disturbance to be rejected perfectly. So how do we do that? Let us for instance pick the controller structure C of s to be of the form C1 of s divided by s square plus omega square, where C1 of s is a controller that we still need to design, but it would be designed in such a manner that our closed loop system would be stable. So in other words, what we have made sure with this choice is that we have ensured that we have the term s square plus omega square in the denominator polynomial of our controller transfer function C of s. Now suppose we choose a controller of this form, then x of s can be written as x of s is equal to a1s plus a2 divided by 1 plus c1 of s times p of s divided by s square plus omega square times s square plus omega square. and this upon simplification would become a1s plus a2 divided by s square plus omega square plus c1 of s times p of s divided by s square plus omega square times s square plus omega square. Now what we note here is that we can cancel out the two s square plus omega square terms in this expression and therefore get x of s to be equal to a1s plus a2 divided by s square plus omega square plus c1 of s times p of s. Now what have we achieved in the process? We have managed to get rid of the term s square plus omega square from the denominator polynomial of x of s. Now what we have as a denominator polynomial instead is this term s square plus omega square plus c1 of s times p of s, and all we need to do is to design c1 of s in such a manner that the zeros of this denominator transfer function s square plus omega square plus c1 times p are all on the left half of the complex plane. Now if we do that, then what can be done is to write x of t as Laplace inverse of b1 by s plus p1 plus b2 by s plus p2 and so on and so forth plus bn by s plus pn. There will be, now we will not have the two terms related to s plus j omega and s minus j omega because that has been removed from the denominator polynomial by our specific choice of our controller structure. Now when we take the Laplace inverse of this, we would get this to be equal to b1 e power minus p1t plus b2 e power minus p2t and so on and so forth plus bn e power minus pnt. Now in the limit that t tends to infinity, we would have x of t to be equal to 0, and that is because all of these are decaying functions of time. So if we wait long enough, all of them will die down and our ultimate x of t will be equal to 0. So what this indicates is that although we cannot perfectly reject this disturbance from the time t equal to 0, so instantaneous rejection of disturbance is not possible. If we wait long enough, then we will be able to eventually completely get rid of this disturbance. When I say long enough, I mean that we have to wait for a time scale that is determined by the closed loop bandwidth of our control system. So if we wait for that length of time, then we would be able to perfectly reject this disturbance, which is the most attractive feature of this particular strategy. And the central feature of this strategy was to choose a form for the controller as given here, c of s is equal to c1 of s divided by s square plus omega square. In other words, we have included the denominator polynomial of the disturbance as part of the denominator polynomial of the controller. Now let us try to implement this technique for the particular control system that we were talking about. So in our control system, I have already shown you the structure of the plant and the controller. So our plant has this particular transfer function and our controller has that particular transfer function. So suppose we want to implement this technique for this controller. So what I wish to do is to have a controller c of s to be of the form c1 of s divided by s square plus 10 square. Why did we choose 10? That is because that is the frequency of the disturbance that we want to reject in this particular case. Now can I uncritically choose this as our controller structure, where c1 is the controller we have already designed. So we have already designed a PID controller to take care of our disturbance rejection at 0.2 radians per second, reference tracking at 0.1 radian per second and all of that. Now can I simply cascade that controller with a term 1 by s square plus 10 square and hope that our closed loop system would be able to reject perfectly this disturbance at 10 radian per second. Actually if you think for a little bit, you will discover that you will run into problems if you directly implement it in this manner. Why is that so? That is because of the kind of effect that this term 1 by s square plus 10 square will have on the magnitude and the phase characteristics of the overall Bode plot. So let me briefly plot the Bode plot of the term 1 by s square plus 10 square. So if we have s square plus 1 by s square plus 10 square as our transfer function, to plot the Bode plot I have to substitute s is equal to j omega, in which case I would get this to be 1 by minus omega square plus 10 square. If I were to draw the Bode plot of this transfer function, so the x axis will be log of omega, the y axis will be log of magnitude of 1 by minus omega square plus 10 square, and the phase, the second plot would be the phase of 1 by minus omega square plus 10 square and log of omega. Then I would have that for low frequencies, when omega is much less than 10 radian per second, I would have the gain of this controller to be just 1 by 10 square, which is 1 by 100, so which is minus 40 dB, so it is going to be somewhere here. And as I approach the frequency omega equal to 10 radian per second, my magnitude plot will start to increase, and at exactly omega equal to 10 radian per second, the gain of this transfer function 1 by minus omega square plus 10 square will be infinity. So this will blow up at 10 radian per second. Then again it will drop for frequencies beyond that, and for very large frequencies omega it will go down, the magnitude will go down as 1 over omega square. So it will go down at the rate of minus 40 decibels per decade. How about the phase characteristics? You see from by inspection that when omega is less than 10 radian per second, we would have this transfer function 1 by 10 square minus omega square to always be a positive number, positive real number, which means that its phase will be 0 degrees. And when omega is greater than 10 radian per second, we would have its phase to be a negative real number, which means that the phase will be 180 degrees, minus 180 degrees. Therefore the phase response will start at 0 degrees and stay at 0 degrees up to 10 radian per second, and at 10 radian per second it will abruptly jump from 0 radians to minus 180 degrees or equivalently minus pi radians. So this is the phase characteristics. Examining the magnitude and the phase characteristics will immediately reveal to you the problem with this controller. Since the phase is changing by 180 degrees at 10 radian per second, if our controller C1 of S has even a small phase lag, then it would cause the overall phase to change from that particular value of phase lag to minus 180 degrees plus that particular value of phase lag, which means that you will have the phase crossover necessarily happening at 10 radian per second because of addition of this term. And the gain of the controller at 10 radian per second would be multiplied by infinity, because the gain of this term 1 by 10 square minus omega square at 10 radian per second is infinity, which means that at the phase crossover frequency, which will now be 10 radian per second, you will have a very large open loop gain, which means that your closed loop system is going to be unstable. So how do we avoid this problem? We avoid this problem by choosing a controller C of the kind C1 of S, which is the PID controller that we have already designed, times S by 10 plus 1 the whole square divided by S square by 100 plus 1. So I have written 1 by S square plus 10 square in this particular manner, and there is no loss of generality in writing it in this particular manner. Now what is the advantage of choosing this particular structure? We discover that in the numerator we now have the term S by 10 plus 1, and this term will add a phase lead of plus 45 degrees when omega is equal to 10 radian per second. And since we have two such terms in the numerator, or in other words we have S by 10 plus 1 the whole square, we would get a plus 90 degrees phase lead that is contributed by these two terms. So therefore if I were to plot the Bode plot of just this part alone, namely S by 10 plus 1 the square divided by S square by 100 plus 1, I would discover that the magnitude plot is log frequency. The magnitude plot at very low frequencies omega will have a gain of 0 dB, because in the numerator as well as in the denominator I can ignore the terms related to omega, and I would have 0 dB, and as I approach omega equal to 10 radian per second, my gain will increase and it will be infinity as before, and it will come back for frequencies beyond 10 radian per second, but it will not decay at minus 40 dB per decade as it happened in the previous case, because when for omega much greater than 10 radian per second, we would have this term to be approximately equal to omega square j omega the whole square by 10 square divided by j omega the whole square divided by 100, which is once again going to be equal to 1, which means that this controller's magnitude characteristics will come back to 0 dB beyond 10 radian per second. As far as the phase is concerned, the initial phase will be close to 0 degrees as before, and there will be an increase in phase contributed by the term s by 10 plus 1 as we approach the frequency 10 radian per second. So there will be an increase in phase and an abrupt change in phase of minus 180 degrees introduced by the term s square by 100 plus 1 at the frequency 10 radian per second. So there is an abrupt change in phase, and then subsequently there will be an increase in phase. So this term s by 10 plus 1 will eventually approach plus 180 degrees phase lead. So that will cancel out the minus 180 degrees phase lag contributed by the term s square by 100 plus 1. So eventually the phase will asymptotically approach 0 degrees once again. So this is the angle of this particular transfer function as function of frequency. So what we see is that this term here s by 10 plus 1 the whole square divided by s square by 100 plus 1 modifies the controller's Bode plot only in the neighborhood of 10 radian per second. It increases the gain, in fact at 10 radian per second it makes it infinity, and it modifies the phase also in the vicinity of that frequency alone and leaves the rest of the frequency range untouched. And that is precisely what we desire, because we have already designed our PID controller C1 of S to give us the required stability and performance specifications in the other frequency ranges. So with this modification to our controller structure, let us see how we are able to fare. First, I have plotted here the Bode plot of this overall system. So what you see in the red dashed line here is the Bode plot of our open loop system, namely the plant times the PID controller, or in other words the controller that has only these 3 terms here, and that is given by the red line. And this was something that we designed a few clips back when we were discussing design using Bode plots. Now what we have done is we have cascaded the term s by 10 plus 1 the whole square divided by s square by 100 plus 1 to this controller, and as we discussed, that modifies the Bode plot of the overall open loop system only in the vicinity of 10 radian per second, and in particular at 10 radian per second the gain has now become infinitely large. The phase response also is along the lines that we discussed in the previous slide. So the phase starts to increase in relation to the original phase characteristics because of the term s by 10 plus 1, and there is a sudden change in phase by minus 180 degrees introduced by the term s square by 100 plus 1, and then the phase will continue to increase and asymptotically approach the original phase response of the overall open loop system. So this is how it looks, and from this we can understand why we can expect perfect rejection of disturbance because of this controller. That is because at 10 radian per second we are having a loop gain of infinite dB, and infinite loop gain is the key for us to get perfect control performance, either perfect tracking of references or perfect rejection of disturbances. In this case I have carried out a simulation where we have compared the performance of the closed loop system in the absence of this controller. So this is the original PID controller that we had designed a few clips back, and we discussed that we were able to bring down suppress a disturbance by 99%, 98% exactly as we had desired it to be, although it was not completely suppressed. However, now with the new controller where we have included the new term 1 by s square plus omega square in the denominator of the controller, and we have also modified the numerator of the controller so that this new term does not affect the frequency characteristics at frequencies other than 10 radian per second. If I were to plot the closed loop response of the system to the same disturbance at 10 radian per second, what you see is here. So we see that there is an initial transience, a small transience, but after the transience is passed, the system does not at all respond to this disturbance. So in other words, we have succeeded in perfectly rejecting disturbance at 10 radian per second by using this controller. If you look at the closed loop transient responses of the system, for the first case we had a certain transient response. This was something we discussed a few lectures back. I am just reproducing it here for the sake of continuity, and with the present controller we get a similar transient response with a slightly higher overshoot because the phase margin has dropped a little bit as a result of this controller, but we can always add a lead compensator to improve the phase margin as we have discussed a few clips back, and therefore this slight increased overshoot is not too much of a problem for us. So at the heart of what we accomplished now was our choice of this controller structure. We chose our controller to be of the form C of S is equal to C1 of S divided by S square plus 10 square, or more generally if there is a disturbance at a particular frequency omega, then we choose the controller to be of the form C1 of S divided by S square plus omega square. So with this choice we were able to reject this disturbance perfectly, and this very neat elegant trick has a name. It is called internal model principle. So the principle states that a signal R of t or a disturbance d of t can be rejected perfectly in steady state if the denominator polynomial of R of S, which is a Laplace transform of R of t, or D of S is included as part of the denominator polynomial of the controller C of S. So if we include the denominator polynomial of R of t or D of t as part of the denominator polynomial of our controller C, then we can in steady state reject that disturbance perfectly or track that reference perfectly. So this is called the internal model principle, and this is widely used in industry in scenarios where you either know the disturbance very well if it is a periodic disturbance, so that we know that its frequency spectrum is characterized by discrete energy content in discrete set of frequencies, then we can employ internal model principle to perfectly reject the disturbance in steady state. Similarly, reference tracking of sinusoidal inputs or other periodic inputs can also be accomplished with zero steady state error by using internal model principle. Now suppose we wanted to apply internal model principle for another case, namely the case of reference tracking, and suppose we had a reference at around 50 radians per second that we wanted to track. So 50 radians per second would be somewhere here. We see that the loop gain is not high enough in this frequency range because this is the mid frequency range of our system, and therefore without this internal model controller we will not be able to track this reference perfectly. So what I have done therefore is to incorporate this internal model term in as part of the controller. So this is the tracking performance of the controller without the internal model term. So I do not have a term of the kind 1 by S square by 50 square plus 1 as part of the denominator polynomial of my C of S, and without it you see that there is a noticeable error between the reference that you have provided at this frequency, namely 50 radian per second, and the response at that frequency. However, suppose we were to modify the controller to include this term. So now we have the term S square by 50 square plus 1 as part of the denominator polynomial, and in this case I have not chosen to add the 0 exactly at 50 radian per second, but I have chosen it to be added at slightly lesser frequency, around 35 radians per second, with the hope of getting a slightly extra phase lead at 50 radian per second for the overall open loop system. So with this controller we see that there is an initial transient. So initially of course the two are not matching perfectly, or in other words the reference is not tracked perfectly, but after the transients has dried down you see that the reference and the output sit almost exactly one on top of another, which indicates that this controller is able to perfectly track this reference with 0 steady state error. Now suppose we have, let us say, a reference R of S which can be written as a numerator polynomial NR of S divided by denominator polynomial dr of S, and suppose we have a disturbance D of S which can be written as the ratio of a numerator polynomial Nd of S and a denominator polynomial Dd of S. If you want to track this reference perfectly and reject that disturbance perfectly at the same time, then what we need to do is choose a controller C of the form C of S is equal to C1 of S divided by the least common multiple, or in other words LCM of dr of S and dd of S. So with this choice of a controller structure where C1 is designed to ensure that our closed loop system is stable and it meets other performance specifications at other frequencies for disturbance rejection and so on, we can make sure that this reference, this specific reference R of S and this particular specific disturbance D of S can be tracked perfectly and rejected perfectly respectively by using the internal model principle.